Tēnā koutou katoa. Welcome back to a brand new video. Today we are going to be evaluating the same infinitely nested integral, but from 1 to 1 plus e. And we are going to make some assumptions from our last video, which I will link below, where we found the indefinite integral of this function. And we are going to begin by doing essentially the same steps. So the first thing we notice is if we take the integrand to be f, then we get the natural log of x take away the natural log of x infinitely many times. And therefore we can actually allow this to be the natural log of x take away f. Because it's infinitely many times, it's sort of a function of itself. And therefore, if we take the exponential of both sides, we get e to the f is equal to x minus f. And hence we get x is equal to e to the f plus f. And from here, we're going to do this a bit differently in terms of finding the definite integral from here on out. Last time we differentiated and found we found a substitution for dx in terms of dy, so we could integrate in terms of y instead of x. This time we are going to actually integrate this function of x directly. And what this will describe is the area enclosed between the function and the y-axis. Okay? And we can use a bit of geometry to find the area enclosed between the function and the x-axis, and that would actually complete our answer here. And I will show you guys on Desmos at the end of the video that this is true and that this converges to the answer we find, whatever that will be. Okay, so let's go ahead and think about this. We want to integrate this thing in terms of limits. And we have the limits here, x is equal to 1 and x is equal to 1 plus e. So what's some possible limits of f that allows this to happen? Well, I picked these limits intentionally so it's easy to find values of f. If it wasn't that easy, then we'd have some problems and we'd probably have to write out an approximation series, or we could even use Newton's method somehow, but we are just going to do it this way with some easy limits. So to have x is equal to 1, all we have to have is f is equal to 0, because that way we get x is equal to 1 on the right hand side. So f is equal to 0 is our lower limits. And to have 1 plus e, we just substitute in f is equal to 1. So these are our limits of integration for our integral. So we get from 0 to 1 of e to the f plus f df is our integral. And again, that will find the area enclosed between our function and the y-axis. And now let's have a think. What would this converge to? Well, that would easily just become e to the f plus f squared over 2 evaluated between 0 and 1. And that is just going to give us e plus a half. And then we also get minus 1. So that will give us e minus a half. And now this is where we can apply a bit of geometry in terms of integrals. Let's take an approximation of what our function would look like. It has an intersection at 1, 0, and it increases the rest of its domain. Okay, and we're interested from 1, 0 to the point 1, to 1 plus e 1. 1 plus e 1. Okay? We want to find this area, but we have essentially this area. And what you can see is something quite interesting here. We have a rectangular region. And this is 1 plus e. And all this is the height. So we can use a bit of geometric reasoning to show that the integral here from 1 to 1 plus e of that ever bounding function on the x-axis is going to equal xy, our height, times the width, take away this area, which is just our integral that we found, which is from 0 to 1 of e to the f plus f df. And we've actually already found that answer, so we can just directly substitute that in. So we get xy take away e minus a half, and we can plug in our values here for x and y, and we just get 1 plus e minus a half. Plus a half, sorry. I need to expand that half. Negative into the negative half as well. And that cancels with that, and we get 3 over 2. And now I'll just pull up Desmos, where I've got as many logs as I can actually put onto Desmos, and we'll show that, hey, it's going to converge about here. So now we've got this up. We have this representation of the integral from our infinitely nested function from 1 to 1 plus e. If we were to keep adding new terms up to infinite terms, it will converge to that 3 over 2 answer that we got. So if I add new terms, you see it alternates. But it's getting closer and closer to 3 over 2. So therefore, the answer is correct. So in the next video, I will make a generalization, or try to make a generalization of this integral using these properties to see if it is possible to find the definite integral over a continuous period on this function for any interval. So for example, from 1 to 2.